Welcome back to multivariable calculus. In this video, we're going to talk about planes in 3 dimensions and how to work with planes using equations of planes. So we are going to be given some plane of some sort, and we want to describe it using some type of equations. There are several types of equations we're going to talk about, such as the vector equation, the scalar equation, the linear equation of a plane. And then once we know how to work with planes, we're going to use some applications. We're going to do some applications such as finding the distance from a point to the plane. So how are we going to describe planes? Um, a plane in 3D is actually determined by any 3 points. So if I have 3 points, say P, Q, and R, that's going to describe a plane in 3 dimensions. But what I want to do is, well, give myself some sort of equation that is going to allow me to actually work with this plane. So we're going to use vectors for that. What we're going to do is figure out, for example, from P to Q, there is a vector. From P to R, there is a vector. And we are going to be able to describe this plane by the perpendicular vector to those vectors. So a perpendicular vector to the plane itself, which we're going to call the normal vector to the plane. And so that given a point and a perpendicular vector, we're going to be able to describe the plane as, well, what are the points on the plane? A point is on the plane, for example, Q is on the plane if the vector from P to Q is perpendicular to N. So for any other point, for example, R, this point is on the plane because the vector from P to R is perpendicular to N. So what we're looking for is a point Q, say, given P and the normal vector, I want a point Q such that the normal vector is perpendicular to the vector from P to Q. And we know how to express this using the dot product. What we're looking for is a point Q such that N dot product with the vector from P to Q, that gives me 0. And the point is that the plane is precisely described by all the points Q such that the normal vector is perpendicular to the vector from P to Q. So let's do exactly that. So let me show you how to come up with the vector and a scalar equation of a plane. We have a fixed point P naught with coordinates x naught, y naught, z naught, and I'm giving a perpendicular vector, a normal vector, which is the vector n with coordinates a, b, c. And I want the plane that is perpendicular to n, and it goes through a point P naught. Then, as I said before, any other point has to have the property that the vector from P naught to P is perpendicular to the vector n. So the position vector for P naught is R naught, which has the same coordinates, x naught, y naught, z naught as P naught. And the position vector for the point P is just R, and it has coordinates x, y, and z. Then the vector from P naught to P is given by R naught, R minus R naught, that is the vector, but the vector from P naught to P, and that is given by the difference of x minus x naught, y minus y naught, z minus z naught. Now, the vector equation is simply saying that r minus r naught has to be perpendicular to the vector n. And we express that using the dot product. Remember that the dot product is 0 if and only if the two vectors are perpendicular. So this relationship of vectors is what we call the vector equation that describes a plane. And if we express that in terms of, well, the coefficients that we have described here, that says that x minus x naught, y minus y naught, z minus z naught, dot product with ABC has to be 0. And if I expand that dot product, what I get is that A times x minus x naught plus b times y minus y naught plus z times z minus z0 is equal to 0, this is what we call the scalar vector, the scalar equation of the plane. Okay, here's an example. Let's find the scalar equation of a plane that goes through P, that is 1, 0, 0, and it is perpendicular to the vector n 0, 1, minus 1. So here we have this would be our P naught in the other notation. So the position of P is just the unknown x, y, z. The point P naught is the point 1, 0, 0. The vector from P naught to P is the difference between the coordinates, the position vector for P and the position vector for P naught. So that would be x, y, z minus 1, 0, 0. And then that is x minus 1, y minus 0, z minus 0. And then what we want for the vector equation is that P naught P, this vector, has to be perpendicular to the normal vector, or in terms of the dot product, that this vector dot n is 0. So that would be the vector equation. And then if we put that in coordinates, that says that x minus 1, y minus 0, z minus 0, dot product with 0, 1, minus 1 has to be 0. And if I expand this, 0 times x minus 1 plus 1 times y minus 0 minus 1 times z minus 0 equals 0, this is what we call the scalar equation of the plane. Now, what we're going to do next in a moment is that I can simplify this equation, just simply expand all those parentheses or distribute the coefficients with the parentheses and get a simpler equation, which in this case, we can do that here. 0 times this is 0, 1 times y, I just get y, and minus 1 times z, I get minus z. So this equation right here, the one in yellow right now, it is the scalar equation. And this one that I just got is what we're going to call the linear equation for my plane. This is the linear equation. Here I've written in Desmos the equation, the vector equation of the plane we were talking about. And here you can see I'm rotating it so you can get a sense of how it sits in 3D. This is the plane. And as I said, I've simplified it also into what's called the linear equation. And I'm going to click on it so you can see it too. There's no difference other than that it just changed color because now there is another plane. It's exactly the same plane as the plane y minus z equals 0, and this is what it looks like. Okay, so now I can tell you how to go from the vector to the scalar to the linear equation of a plane. Remember that we had essentially what we call the position for P minus the position for P naught dot n equals 0. That is what we call the vector equation of the plane. If I put this in coordinates, then this is x minus x naught, y minus y naught, z minus z naught, dot a, b, c is 0. And if I expand this dot product, what I get is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And again, this is the vector equation. This one here is what we call the scalar equation. And then you can see that I can simplify this simply by expanding those parentheses or just distributing the constant in here, and I'll get a times x minus a times x naught. A is a number, x naught is a number, so a times x naught is a number. And what I'm going to get is ax, by, cz plus some other number when I put together all the other constants together. So what I'm going to get is an equation of the form ax plus by plus zz plus some other number d equal to 0 once I simplify everything. And this equation right here is what we call the linear equation, because it's given by one linear equation in the variables x, y, and z to the first power. And one thing to remark is that the coefficients a, b, c in the linear equation are the coefficients of the normal vector. Okay, so let's see an example. In this example, I'm going to find the linear equation of a plane that goes through a point 2, 4, minus 1, and is normal to 2, 3, 4. I can start from, say, the scalar equation. I know that the scalar equation is going to be the coefficients of the vector times x minus the x coordinate of the point, plus 3 times y minus the y coordinate of the point, plus 4 times the z minus the third coordinate of the point. Now, this is the vector, this is the scalar equation of the plane. If I multiply through, I'm going to get 2x minus 4 plus 3y minus 12 plus 4z minus 1 is plus 1, so I get plus 4 equals 0. And now if I simplify these farther, I'm going to get 2x plus 3y plus 4z, and then minus 4 and minus 4 and plus 4 cancel out, so I get just a minus 12. So this equation is the linear equation of this plane. And we can do a couple of checks. I'm going to check, first of all, one check is that it has to be a plane normal or perpendicular to 2, 3, 4, and 2, 3, 4 should be the coefficients that appear in front of the x, y, and z. That is true. And second, it has to go through this point. So I can check that P is in the plane. The P belongs to the plane. So in order to check that P belongs to the plane, I just have to substitute the values of the coefficients of the point in terms of x, y, and z, and check that they do satisfy this equation. So let's see, 2 times the x coordinate plus 3 times the y coordinate plus 4 times the z coordinate, which is minus 1, minus 12. That hopefully is 0. So let's see, 2 times 2 is 4, and this minus 4, that will cancel out. 12 minus 12, I do get 0. So the point is in the plane, and it is perpendicular to 2, 3, 4. So I have written the equation of the plane in vector form right here, so you can see it in the graph. And this is what we got when we did the linear equation. So that was the scalar equation. This is the linear equation. I'm going to click on it, and you can see nothing changed because it's exactly the same plane. This linear equation is a simplified form of the vector equation, and therefore it just gives the exactly same plane in 3 dimensions. Let's continue, and now we're going to find the equation of the plane that passes through the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. So now we're not given the normal vector, but we can find out using, as you remember, using the cross product. So the vector from P to Q is given by the coordinates of Q minus the vector position for P. So it is 0, 1, 0, minus 1, 0, 0. So it is the vector minus 1, 1, 0. And similarly, the vector from P to R will be the position of R minus the position of P, which is 0, 0, 1, minus 1, 0, 0, which will give me the vector minus 1, 0, 1. Now, to compute n will be a normal vector to those two. So what I'm going to do is the cross product of PQ by PR to get a normal vector, one that is perpendicular to both. And remember, I can write determinant ijk. The first row is just going to be the vector PQ, and the second row is the vector PR. And remember that we expand those determinants, and it's I times the determinant 1, 0, 0, 1 minus j times the determinant that you get when you cancel out this row and this column. So the determinant minus 1, 0, minus 1, 1 plus k times the determinant that you get when you cancel out this column and this row. So what I get is minus 1, 1, minus 1, 0. And that will be I times, remember these determinants are this diagonal, 1 times 1 minus 0 times 0, so that is just times 1, minus j times, that will be times minus 1 minus minus 0, so just minus 1, plus k times minus 1 times 0 is 0, minus minus 1 times 1. So this vector is in fact the vector I plus j plus k. So what we get here is that the normal vector we were looking for is just the vector 1, 1, 1. So now I can find the equation for my plane by using the normal vector and a point. Let's pick P, 1, 0, 0, and therefore the equation for the plane will be 1 times x minus 1. I'm using the coordinates of P here, and the coefficient, this 1, is from the normal vector, y minus 0 plus 1 times z minus 0, and that is just, well, this has to be equal to 0, and if I expand this is x minus 1 plus y plus z, so equal to 0, or this is x plus y plus z equals 1. So this should be the equation I was looking for. Let's check that all 3 points are in the plane. 1, 0, 0 is in here, 0, 1, 0 is in here, and 0, 0, 1 is in here. And the plane, the coefficients here is 1, 1, 1, so it is perpendicular to this vector. So this is the plane I was looking for. Let's do that again, but now with the 3 points 2, 0, 1, 0 minus 1, 1, and 0, 0 minus 1. Let me give these names. This is going to be my point P, my point Q, and my point R. The vector then from P to Q will be the difference. 0 minus 2, that's minus 2, minus 1 minus 0, that's minus 1. 1 minus 1 is 0. The point P to R will be the vector R minus P. So 0 minus 2 is minus 2 again. 0 minus 0 is 0. And minus 1 minus minus 1, that's minus 2. Okay. And now I'm going to figure out what is the normal vector. The normal vector will be given by the cross product of those two vectors, I, j, k, minus 2, minus 1, 0, minus 2, 0, minus 2. And let's figure what that is. That will be I times minus 1 times minus 2 minus 0 times 0. So this is times 2. Minus j times minus 2 times minus 2, that's 4. Minus 2 times 0 is 0, so times 4. Plus k times minus 2 times 0 is 0. Minus 1 times minus 2 is 2, with a negative sign is minus 2. So the vector that I get here is 2i minus 4j minus 2k, which is a normal vector. This is the normal vector, so this is the vector 2 minus 4 minus 2, which is parallel to I only need a normal vector, so any multiple of this, and since these are all multiples of 2, I can divide by 2, I can scale it, and get this vector. So this is going to be my normal vector that I'm going to use for the plane. I could have used this one, but that's just a multiple of that one, and it's easier to use 1 minus 2 minus 1. So that's the one I'm going to use. And now I can use my vector, my scalar equation for the plane. This will be, I'm going to use that. I'm going to use the point P and my normal vector to write an equation. So this is 1 times x minus 2 minus 2 times y minus 0 and minus 1 times z minus 1 equals 0. Now simplify. This is x minus 2 minus 2y minus z plus 1 equals 0, or x minus 2y minus z equal, this minus 2 and plus 1 is minus 1, and the other side is 1. So if I haven't made any mistakes, this is the equation of the plane I was looking for. First of all, the coefficients are 1 minus 2 minus 1, which is the coefficients of the normal vector. And let's check that the point 2, 0, 1 is in the plane. 2 plus 0 minus 1, that is 1. So this vector, this equation is of a plane that is perpendicular to the normal vector, and it is passing through 2, 0, 1. Let's verify that 0 minus 1, 1, it is also in the plane. If I put 2, 0 minus 1, 1, I get 0. 2 minus 1 is 1. And this is also, r is also in the plane, 0, 0, and minus minus 1 is 1. So all 3 points are in the plane, so this is the plane I was looking for. Now, if I have 2 planes, what are the possible relative positions of 2 planes? The usual position is that 2 planes will intersect at some line. So planes that look like this, and they just intersect. We could also have 2 planes that are parallel. So I can have planes that are exactly parallel. And then I can have 2 planes that are exactly the same plane. It's just I can have 2 equations that are actually describing the same plane. So these could be exactly the same plane. They can be parallel, or they can be intersecting, secant, intersecting. If they are intersecting, I am going to find out what the line of intersection is. If they are parallel, how do I figure out that these 2 vectors are, 2 planes are parallel? Well, I can look at their normal vectors, and they're going to be parallel if they have exactly the same normal vector or a scalar multiple of the same vector. So this is n1, n2, and what is happening is that n1 and n2, so n1 is some multiple of n2, but they are not exactly the same plane if they don't share any points in common. The intersection is empty. Okay, so the intersection is empty. But in the case that they're exactly the same, they will have also normal vectors that are a multiple of each other, and every point is in the intersection. So we'll be able to tell these positions apart by investigating the normal vectors and the intersection. Let's, for example, investigate the relative position of these 3 planes. So to do so, the first thing we need to do is check what are their normal vectors. So from the coefficients of this plane, I can see the normal vector is 1, 0, minus 1, because those are the coefficients for x, y, and z. The coefficients in this case would be 2, 0, minus 2, and then I can see that these two vectors are a multiple of each other. This vector is twice this one. So these 2 planes, the first 2 planes, are going to be either parallel or the exact same plane. So let's see what is the vector for the last one. The last one has vector 2, minus 2, 0, which is not parallel to this one or that one. So let's call these planes, this one M1, M2, and M3. Then M3 is not parallel to M1 or M2, so it intersects M1 and M2. And what about M1 and M2? M1 and M2 would be parallel if they don't have points in common. So let's find one point in M1. N1 has a point. For example, if I put 2, 0, 0, that is a point on M1. Let's see if this point is on M2. So if I plug in this point in the equation for M2, what happens? But 2, 0, 0, if I plug in 2 times 2 minus 0, that is 4, is not equal to 5. So that point is not in M2. So M1 and M2 are parallel but not the same. M1 and M2 are parallel but not the same plane. Okay, so let's figure out now the angle between two planes. So if they are not parallel, what is the angle between them? So how I'm going to figure that out? So suppose I have a plane, I have some other plane, and I want to know somehow what is the angle between these two planes. And what we're going to do is, well, I have some normal vector here for one plane, and I have some other normal vector for the other plane. So this is the plane, say, M1, M2. M2 has normal vector N2, M1 has normal vector N1. And what I'm going to do is just measure the angle between the normal vectors. And remember that I know how to compute angles using the dot product. So I can get to theta by doing the dot product of N1 and N2. Remember that is the length of N1 times the length of N2 times the cosine of theta, or that cosine of theta is the dot product of the normal vectors divided by the length of the normal vectors, the product of the lengths of the normal vectors. So let's see an example. Let's find the angle between the planes x plus y plus z equals 1 and x minus z equals 3. So remember what we just said is that to do that, what I'm going to do is find the normal vectors. The normal vectors are given by the coefficients of x, y, and z. And the normal vector here, which is 1, 0, minus 1. And then the cosine of the angle between them will be given by the dot product divided by the length of N1 times the length of N2. So let's do that. What is the dot product? The dot product will be 1 times 1 plus 1 times 0 plus 1 times minus 1. And the lengths, well, the length of N1 is the square root of the square of the coefficient. So 1 squared plus 1 squared plus 1 squared times the length of the other one, which is 1 squared plus minus 1 squared. So this is, you see, 1 times 1 plus 0 plus minus 1. This is 0, so in fact, this is a square root of 3, this is a square root of 2, but because there's a 0 in the numerator, this is just 0. And when the cosine is 0, that implies that theta is pi over 2, which means that the two planes are perpendicular. So the planes are perpendicular. And I can show you that in Desmus. So here in gray is the plane x plus y plus z equals 1, and in red is the plane x minus z equals to 3. And if you look at it from the right angle, you can see that these two planes are in fact perpendicular to each other. Since we found that these two planes are actually perpendicular, then there is a line of intersection between them, and I can parameterize it, and we can figure it out what the line is. It has to be a line that is given by the intersection of these two planes. So it has to satisfy both equations at the same time. So what I can do is, from this equation, I can see that I can solve for x in terms of z. This is 3 plus z. And if I plug it into the first equation, that is 3 plus z plus y plus z equals 1, which tells me that I can solve for y in terms of z. That will be minus 2z. So all in all, I can write everything in terms of z, or if I give to z a parameter, then I know that x is 3 plus z, so it is 3 plus t. And if I already know that y is minus 2z, then y is minus 2t. So this is a parametric equation for the line that is the intersection of the two planes. And I can show you this in Desmus. Again, in gray is x plus y plus z equals 1. In red is x minus 3 equals to x minus z equals to 3. And I have parameterized the line that is at the intersection. And you can see it is in blue. Let's turn it around like this. So you can see the line in blue is precisely the intersection. Let me undo the planes themselves. And that is the line that is in the intersection. If I bring the planes back, that plane goes through that line, this plane goes through that line, and it's all the points that are at the intersection of the two planes. Now let's do another example of an angle and the line of intersection between two planes. So let's see first what is the angle. Here, the normal vector is given by 1, 0, 1. The normal vector here is 1 minus 1, 0. So the angle between the planes will be the cosine of the angle between those two vectors. The dot product is 1 times 1 is 1, 0 times minus 1 is 0, 1 times 0 is 0. So the dot product is just 1. The length of 1, 0, 1 is the square root of 1 squared plus 1 squared, so it's the square root of 2. The length of 1 minus 1, 0, it's also the square root of 2, so this is a half. And what angle has cosine of a half? Well, it is the angle that has the sine is the square root of 3 over 2, and the theta is a half. So that tells me that theta in this case is 60 degrees. So pi divided by 3, or 60 degrees. Great. So I have the angle, and what about the line of intersection? The line of intersection will be given by the intersection of the two planes. And in this case, since x is in both equations, I'm going to take x to be t. Then x plus z equals to 2 tells me that z is 2 minus x, so it is 2 minus t. And this last equation tells me that y is x minus 3, or that y is t minus 3. So all in all, the line is given in parametric equations as x equals t, y equals t minus 3, and z equals 2 minus t. So this is the line of intersection in parametric form. Finally, the last topic in this video is finding distances from a point to a plane. So here what we're going to do, how do we do that? If we start from a plane, we know the equation for the plane. So we know a normal vector, and I have a point that is not on the plane. Now, what we can do is go perpendicularly from this point P1 to the plane and measure the distance from the point to the plane. So how do we actually do that is by finding the equation of the line that goes from P1 in the direction of the normal vector, and then find what point is at the in the plane in that line, and then find the distance between that point and the point of intersection. I'm not going to elaborate on that and figure out how the formula comes about, but here is exactly the formula that one gets. The distance from a point P1 to the plane given by this linear equation is exactly this formula. So let's see an example. So here we're going to find the distance from the point 1, 2, 3 to the plane x plus z equals 2. And the formula is pretty easy once you know what the formula is. So we want the absolute value of a times x1. So remember, these are the x1, y1, z1, and here the normal vector. The normal vector is in this case 1, 0, 1, and those are the coefficients a, b, c. So we have a, so 1 times x1, so 1 times 1 plus 0 times 2 plus 1 times 3 plus, we have to put this equation in the form x plus z minus 2 equals 0, and then the last coefficient here is not plus 2 but minus 2, and in absolute value divided by the square root of this is the length of the normal vector, so this is 1 squared plus 0 squared plus 1 squared. So if I simplify, I should get the absolute value of 1 plus 3 is 4 minus 2 is 2 divided by the square root of 2. So this is 2 divided by the square root of 2, which is the square root of 2. So the distance from the point to the plane is just a square root of 2. Okay, so now let's use the distance formula to find the distance between two parallel planes that are not identical. We saw this before, that this plane, x plus z equals to 2, and 2x plus 2z equals 5. I had a typo here before. These two planes are parallel and not the same because they have the same normal vector, but they don't have the same points. So what that means is that I have a plane and I have another plane, and they are parallel, but I want to find what is the distance from one plane to another. So if I go perpendicularly from one to the other, what is this distance? Since I know how to find the distance from a plane to a point, all I need to know is, well, I need a point here, and I have a plane down here, 2z equals 5, and then use my distance formula. So that's exactly what I'm going to do. What is a point in here? That point can be, for example, 1, 0, 1. That is a point over there. And here's my formula for the plane. The plane is 2x plus 2z minus 5 equals to 0. So then the distance formula will be the point 101 evaluated in the plane. So that is 2 times 1 plus 2 times 1 minus 5 divided by the square root of the vector that is the normal vector to my plane. So here is 2, 0, 2. So 2 squared plus 0 squared plus 2 squared. The numerator is 4 minus 5 is minus 1, and absolute value is 1, and the denominator is the square root of 4 plus 4, 8. So it's the square root of 8 which I can simplify. That would be 2 times the square root of 2. So 1 over the 2, the square root of 2 is the distance that I wanted, the distance between the two planes. Okay, so next time we're going to be talking about quadric surfaces. We're going to be talking about cylinders and quadric surfaces and how to draw surfaces in 3D. Until then.